Composite beams. So first of all, let's look at what are composite beams. Okay, a composite beam is a structural member made from two or more different materials joined together to carry a load acting on it. The load is perpendicular to the longitudinal axis, and this is how we define beams. Right? So you can see that the composite beam consists of two or more different materials joined together, and we assume that they are perfectly bonded together without interfacial sliding. In this chapter, we only consider simple cases, just two materials. Okay, we will not deal with more than two materials. Okay, so examples in practice of composite beam will include concrete slabs supported by steel beams, or you have half concrete, half steel put together as a beam. Right? Plywood beams, reinforced concrete beams, composite cantilevers, etc. These components have to be fully bonded, fully connected to form a composite beam. As I mentioned, this just means that you're not allowing any interfacial sliding. Composite beams have many advantages. That is why they have been frequently used in practical designs. Okay, they normally can provide you higher strength, which improves safety. They can provide higher stiffness. This will reduce the deflection that is critical in large span beams. Okay, since when you have a large span structure, you will not want to see the seenable, observable deflections or deformations. Right? It can provide you better durability, since one material can protect another material, like steel reinforced concrete. Here, the steel reinforced concrete serves as a perfect example to explain this. Okay, so you may not know that concrete is a brittle material. Right? It's a brittle material which is easy to crack. Okay, so normally when we design a concrete structure, we use steel to reinforce the concrete. And steel is ductile, concrete is brittle. So we leverage the ductility of steel to provide the overall ductility of reinforced concrete structural members. But steel is easy to be corroded when it's exposed to moist air, but concrete will not corrode, right? So we use concrete to wrap steel to protect the steel from being corroded. So you can see that the steel reinforced concrete seems to be a perfect design, okay? Invulnerable design, like Achilles. Right? If without the heel, it will be perfect. Right? So the steel reinforced concrete serves as a perfect example of better or perfect durability of composite materials. And in some cases, it will provide lower cost. Okay, these are the advantages of composite beams. Now let's look at the mechanical stuff of composite beam. As we have talked about the flat plane assumption, this assumption also holds in composite beams. Okay, this assumption told us that the strain distribution will follow this figure. Right? The strain is 0 at the neutral axis. Okay, if you have a composite beam, 50-50% composite beam with different materials in which the modulus of elasticity of 1 is lower than that of 2. So the neutral axis will not be in the middle. Right? The neutral axis will move to the harder parts, to the parts, the section having larger modulus of elasticity. So you can see that the neutral axis is not in the middle. Okay, but the strain is always 0 at the neutral axis, and linearly increasing by moving away from the neutral axis. This is the flat plane assumption, right? And according to the flat plane assumption, the strain are the same at two sides of the interface, the fully bounded interface. As you can see here, this is the interface, right? On both sides of this interface, the value of strain should be the same. Should be the same. that is strain, right? Just the flat plane assumption only deal with strain. Okay, the strain is continuous. Okay, strain is continuous, meaning that the strain is the same at both sides, at two sides of this interface. But how about stress? Okay, if the strain is the same, then their stress will not be the same, right? Since they have different modulus of elasticity. According to Hooke's law, the stress just equals strain times their modulus of elasticity. Since E1 is smaller than E2, so the stress 1 will be smaller than stress 2. Okay, so the stress is 0 at the neutral axis. That will be valid because the strain is 0. Right? Strain times any modulus of elasticity will be 0. The stress is 0 at the neutral axis and linearly increasing by moving away from the neutral axis before reaching the interface. Stress are different at two sides of the interface according to Hooke's law, as we just explained here. Right? So keep this in mind. Then let's look at the transformed sections. Okay, the bending stress equation, this equation, sigma equals m times y over I. This equation is only valid if the stress distribution is linear. Okay, if the stress distribution is not linear, as shown here, through the interface is not continuous. Right? In this case, we cannot use this equation to calculate the stress. To make it linear, we can scale the width of a material as one of the materials by a factor n. That is the ratio of a modulus of elasticity. Right? N equals E2 over E1. Okay, to make a transformed section. In this case, we're transforming material 2 into materials 1. Okay, so if we're transforming material 2 into material 1, as shown here, so this material 1 is selected as the base material. Okay, the stress distribution of a transformed section is linear, so the bending stress equation can be used. The stresses at two sides of this interface will be the same in this fictitious case. Why we call it a fictitious case? Because it's not realistic. We're just transformed this material 2 into material 1, as shown here. Okay, we're transformed the material 2 into materials 1. So in the beginning, it's a rectangle cross section, but after transformation, it becomes a T shape. Okay, and we have known how to deal with a monomaterial T shape cross section. Right? We just use these two equations, two tables to determine y bar and I. Then we can calculate the stresses. Right? But the stress on the transformed part will need to be transformed back in the end. Right? After you're calculating the stress in the base material 1 will not need to be transformed, but the stress calculated in section 2 will need to be transformed back. What is the case? As shown here, since this transformed section is larger than the real section, right? Larger than the real section, so its actual cross section is smaller, so the stress should be larger than the calculated value, right? So you need to just time it by a factor n, right? Multiply it by a factor n to transform it back. Okay. Of course, we have two ways to transform the section. We can transform material 2 into material 1, or transform material 1 into material 2. Okay, but the n values will be different. Right? This when you transform the material 2 in material 1, the n1 equals E2 over E1. Right? And N2, if you transform material 2 into material 1 into material 2, the N2 equals E1 over E2. Right? You can see that N1 times N2 equals 1. Right? So 1 is larger than 1, another is smaller than 1. Okay. Well, the general algorithms for composite beam problems are just here, 3 steps. The first step is to transform section, and we can select the base material with modulus elasticity E1 and determine the n. Right, the n equals what? E2 over E1. So we have selected E1 as the base. Then we transform the subsection made with the second material to the base material to multiply the width. Right, this is the key. Multiply the width of this subsection n by n factor and replace it. Okay, as shown here, we are transforming 2 into 1, right? 2 into 1. So this 2 will be, the width of the 2 will become smaller. It's the B2 will become n times B2. You can see that here the n is smaller than 1. Right? N is smaller than 1, meaning what? Meaning E2 is smaller than E1. Okay. Of course, as we mentioned, you can also transform materials 1 into material 2. Right? So in the second case, if you transform 1 into 2, then your n will be E1 over E2. That will be larger than 1, right? So then the B1 will become n times B1. So the shape after transformation will be something like this. Okay, the section 2 will not be changed. This is the section 2, but the section 1 will become larger. Right. It will become something like this. Okay, it's still a T shape, but just a fatter T shape, a wider T shape. Right. Then in step 2, follow the standard procedure for stress analysis in beams and determine the moment, determine the section properties, including Y bar and I, and then determine the stress on transformed section. Since after transformation we have only one material, so just any T shape as shown here, you can just calculate it, and then we can determine the stress distribution as shown here. These are just topics we have covered in previous section. Right, but in the last step, we need to correct the stress on transformed section. Okay, the base section will not need to be changed. Right, the base section 1 will not need to be changed, but the section 2 needs to be changed, transformed back. Okay, the calculated stress sigma 2 prime need to be transformed back to sigma 2. By multiplying the factor n. Okay, you can see that this is a calculated stress. After transformation, you can see at the interface, the stress will be incontinuous. Okay, stress will be incontinuous. It need to be transformed and become smaller. Right, since the n here is smaller than 1. Okay, so this sigma 2 will be smaller than the calculated value. Okay, so then let's give several examples and to practice these theories.